Welcome back. We are discussing the single particle synchrotron spectrum, and we have talked about how the dynamics results in the particle going around in a circle with some angular frequency. We've talked about how, because of relativistic effects, the radiation is beamed into an opening angle of the order 1 over gamma, where gamma is the Lorentz factor of the particle. And we've talked about how, because of geometric effects, we only see the radiation from the particle for a small period of its orbit, and that causes the radiation to kind of pile up. The pulses are shorter than you would expect, and so we derived a characteristic frequency last time, which is the spectrum that I'm going to write down in a second, is going to be in terms of this characteristic frequency. And critically, this characteristic frequency, omega c, where c stands for characteristic and not for cooling, we'll get to that later, has a gamma cubed factor multiplying omega b, and because the omega b has a 1 over gamma, the characteristic frequency is proportional to gamma squared. This omega c gamma squared relationship is one of the most important relationships in the context of synchrotron radiation. So the fact that if you the characteristic frequency of radiation from a charged particle is proportional to the square of its Lorentz factor is very important. You remember that you've seen the gamma square dependence earlier in another context for synchrotron radiation, that is with the power. So the radiation power is also proportional to gamma squared. And that will become important later when we talk about cooling. But here, note that a particle with the Lorentz factor gamma, the higher the Lorentz factor, the higher the frequency that it radiates at. And in fact, the radiation, the characteristic frequency goes as the square of that Lorentz factor. And this will become important because when we talk about multi-particle spectra, we're going to take the entire spectrum of the radiation from a single particle, and we're going to collapse it into a delta function about that omega c. So this omega c is really one of the key aspects of synchrotron radiation from a single particle. All right, so we've gone all around to get to the single particle spectrum, but I've never actually shown you the single particle spectrum. So I'm going to write down the formula for the single particle spectrum. We're not going to calculate it. And then I'll draw the spectrum so that we can get some insight into what is going on. So if you wanted to do this, what you would do is you would take the power, and there are various ways to go about this. You can take the power. So let me just draw a little diagram here. So you can take a single particle power. You can do a Fourier transform of the single particle power, and you can get the single particle spectrum. And then you can integrate this over a particle distribution, and you can get a multi-particle spectrum. Or you can take the single particle power, you can integrate this over the distribution, then you can take the Fourier transform and look at the multi-particle spectrum. You can go over this many ways. The way we're going to do this is you're going to take the power, Fourier transform it, get the single particle spectrum, and integrate it with the distribution. And when I say we're going to do this, I'm just going to write down the results. And I'm not necessarily going to do each of those steps, but I'll describe to you what you would do if you wanted to do each of those steps. Right, so what you would need to do is do that Fourier transform. And so for the Fourier transform, what you need is the power in terms of frequency. And here we actually have a convenient way to do this without needing to actually do the Fourier transform. And that's by taking the Fourier transformed version of Lamar's formula. So you remember the Lamar's formula tells us the power radiated by a charged particle undergoing acceleration. That it has a frequency version as well. And that looks like this. It is E squared, or well, let me be more general and just say Q squared with the charge squared over 3 pi epsilon naught c cubed mod a of omega squared. So what is all of this? So a of omega is, or if you want to be very, very precise, you should put a hat on it. This a hat of omega is the Fourier transform of a of t, where a is the acceleration. So you take the acceleration as a function of time, you Fourier transform that, you get a hat of omega, it will be complex quantity, so you take the mod squared of that. And then, remember the original Lamar's formula had a q squared over 6 pi epsilon naught c cubed, this is 3 pi, and the reason there's a factor of 2 is because this is a real function, so the Fourier transform is Hermitian, and so when you do this, the positive and negative frequency, you add those together. So all of this discussion, if you're interested in following it, is described to you in some detail in section let's see, this is section 8.4.1 of high energy astrophysics. So that tells you how you get this Fourier transform version of Lamar's formula. And you may have seen this in other contexts before. So you can simply take this and you can put in the acceleration, which now you need to Fourier transform. So there's a particle going around a circle, you need to calculate the acceleration, take the Fourier transform. When you do all that, here's what you get. You have two components. There is a J perpendicular. So this J is the emission coefficient. Let me write this down, then I'll describe to you what it is and what it tells us about the radiation. So J perpendicular of omega is root 3 e cubed b sine alpha divided by 16 pi squared epsilon naught c m. And then there are factors here, which I'll write down and then define in a second, f of x plus g of x. And then there's a J parallel of omega. And it looks very similar. It has the same prefactor, root 3 e cubed b sine alpha over 16 pi squared epsilon naught c m. And I notice since we've already written E here, we're talking about electrons. So I'm going to go ahead and put E's on the M's to talk, because there's electron masses, f of x minus g of x. So the only difference between these two are the signs on this G. These are equations 8.56 and 8.57 of high energy astrophysics respectively. And one more thing to keep in mind, that there's an approximation here or an assumption, which is that this is in the ultra relativistic limit. So ultra, which just means that this is in the limit that gamma is much greater than 1, and so we can take beta of the order of 1. Okay, so what is all of this? And I'll describe these f functions and g functions in a second. So this on the left hand side is the emissivity, is the volume emissivity. So it tells you the well, it's actually per particle emissivity. So it tells you the energy radiated per unit time, per unit volume, per unit solid angle by this particle. And well, that's the quantity on the left side. And you see it's a function of frequency. Frequency doesn't appear here. It's buried in here. We'll get to that in a second. Because when we started the discussion of synchrotron radiation, we talked about how the acceleration is, the power depends upon the acceleration squared. The acceleration depends upon, for a given, the acceleration it goes as 1 over mass. And so lighter particles, smaller mass particles are going to have larger accelerations. And so for the rest of our discussion, we're going to focus specifically on synchrotron radiation from electrons. And that is why I put in the E and M here. If you want to generalize this to other kinds of particles, you should replace this E with the charge on the particle and the mass with the mass of the particles. For instance, for protons, this will still be E, but this will be the mass of the proton. For an iron nucleus or some other kind of particle going through the interstellar medium, you should put the mass of the nucleus. And then here you should have the charge on the nucleus, right? So these numbers, or what you put in here, will depend upon the particle that's calculating the radiation for. This stuff. What is this stuff? So this part just tells you the absolute scaling of the power. This part is the interesting part because this is what actually contains the spectrum. Why do I have two of these? One of these are two polarizations. So there are two polarization directions, or two orthogonal polarizations. When we calculate the total power, which is mostly what we're going to be interested in, we're going to add these up. Okay, so what are these F's and G's? Let me just add up these J's to complete the discussion of what I meant by. So this J is J perpendicular plus J parallel of omega, and that is, you add these up, the G's cancel, is root 3 e cubed b sine alpha over 8 pi epsilon naught 8 pi squared epsilon naught c me times f of x. So this, which is equation 8.58 of high energy astrophysics, is the actual total radiation power, and this thing is the spectrum. This contains the information about the spectrum. Okay, so what is f of x? F of x is just a mathematical function of x. What is x? I'll define that. So f of x as a mathematical function is simply x times the integral from x to infinity of a Bessel function of the second kind of order 5/3 z dz, where z is just a dummy variable. So you may have seen these before in other contexts, but Bessel functions are just solutions to the Bessel differential equation, and they are integral orders and non-integral orders, and they are Bessel functions of the first and second kind, depending upon the exact differential equation you're solving. But at the end of the day, they're just mathematical functions, just like the Gaussian function or an x squared function. These are just functions that can't be written down in closed form in terms of like polynomials, but it's still just a mathematical function. So this f of x is just still just a mathematical function of x, and I'll draw it in a second. And the g of x is x times k 2/3 of x, where this k is the same Bessel function of now of a different order. So for our purposes, this x is related, as I said, this is the spectrum, so it must contain the frequency, and so this x is just omega over omega c. Right, so this is the frequency in units of the characteristic frequency. So this is the spectrum of the radiation spectrum, where the frequency is written in units of the characteristic frequency. This will make sense in just a second. Let's look at the shape of f of x. So f of x, it's easier to understand this if we write down some asymptotic limits of f of x. So f of x looks like this. It is, let me just move that a little bit so I can actually fit in the equation that I'm going to write. So f of x is, for small x, looks like this, 4 pi over root 3 gamma 1/3. So this is 1/3. X over 2 to the 1/3 power. This is for x much less than 1. And then for x much greater than 1, it is root pi over 2. Let me just make that absolutely clear. Just write a little larger, root pi over 2 e to the minus x, x to the half. This is for x much greater than 1. So these are asymptotic limits of f of x in small and large x. So you can see that for small x, f of x goes as x to the 1/3, and for large x, f of x basically falls off exponentially. There is an expression for this that is kind of an approximation that is kind of valid for a range of different x, and that's like this. So it's root 3x over 2 to the 1/3 power e to the minus x, and this is valid for all x. It's an approximation across all of x. And you can see small x, this is 1, so it's x to the 1/3. Large x, this dominates, so it falls off exponentially. And so you can see this if you make a plot of f of x. So a plot of f of x versus x in the linear space just looks like this. It's 0 at 0, it rises, and then it falls. And there's a peak. And for this may be relevant to you, this peak is at x is 0.29. That's where this function peaks. And you can, maybe it's a little clearer to do this in log space. So you can plot log of f of x as a function of x. And in that case, you can see at small x, this is just a power law, x to the 1/3. And then it falls off exponentially at about 0.29. For our purposes, by the way, we're going to take the 0.29 to be of the order 1. And so what this means is that the spectrum is peaked close to, remember what is x? X for our purposes is just omega over omega c. So the spectrum peaks at order omega c, and it rises as 1/3 below it at lower frequencies, and it falls up exponentially above it. Okay. So we can verify this. We can verify that this makes sense because this is the spectrum. Now we just spread the radiation out at all those frequencies. We can collect it back across frequencies. We can integrate it out over all frequencies, and we'd better get the total power that's radiated, right, which we already calculated. So we can verify this by writing the total power is the integral of this j omega integrated over all frequencies. And that looks like this. So it's √3 e cubed b sine alpha over 8 pi squared epsilon naught c m e times the integral of f of x dx. So it's f of omega over omega c d omega over all frequencies. And now we need to do this integral. So the way to do that is to multiply and divide by omega c. So that's just a change of variables. And this thing now becomes an integral of f of x dx, which is something that we can calculate. So I'm going to break this up into terms. I'm going to write it like this. So it's 9 √3 over 4 pi, the integral from 0 to infinity of f of x dx times e to the 4th over 6 pi epsilon naught c epsilon naught squared c to the 4th m squared. That's our second term. And then our third term is going to be times c times b squared over 2 mu naught times gamma squared sine squared alpha. So what did I do here? I replace this d omega over omega c by dx, where x is just omega over omega c. And then I put in the expression for omega c, this 3/2 gamma squared qb over m sine alpha. And I put that in here. And then there was a sine alpha already, and there was a b already, so we get a b squared and we get a sine squared alpha. And then there's a gamma squared that comes here, and then there's 3/2 which hits this √3 over 8, and we get 9 √3 over 4 pi. And then there's this factor of 2 I pulled in here. And then there's a factor of c, which I've got because I put in an epsilon and a mu naught in here. So why did I do all of this? It's because we can look at this and we can make sense of this expression. So you've seen all of this before. You may not have seen this before. This I will tell you the value of this. This is 2. What is this? You've seen this before. This is the Thomson cross section. And then this is our magnetic field energy density, UB. The rest of this makes sense. So this is, as expected from before, this is 2 sigma t c UB gamma squared sine squared alpha. And if you remember, the expression for power that we had previously is 2 sigma t c UB beta squared gamma squared sine squared alpha. And the reason we don't have beta squared in here is because this is in the ultra-relativistic limit. So here beta is of the order 1 for these expressions for the emissivity, the single particle emissivity. Okay, so this tells us the single particle spectrum. It's the spectrum depends upon the characteristic frequency omega c, which depends upon q, b, and m. The characteristic frequency, very importantly, is related to the Lorentz factor, and I will write it again. Omega c is proportional to gamma squared, and this relationship is going to become very important when we talk about the radiation from a power law distribution of particles. The spectrum is in units, or is peaked at this characteristic frequency, and it falls off exponentially above that characteristic frequency, and below that frequency it has this 1/3 tail. Another way to think about this, and again it's a derivation we're not going to do, is you remember the cyclotron radiation, if you watched that video or if you've seen it elsewhere, which is a series of harmonics that at the gyro frequency. If you take the cyclotron spectrum, which is for a non-relativistic particle, and you take the particle and you speed it up and you make it go faster and faster, those individual cyclotron lines start becoming broader and they start merging into each other until you get the synchrotron F function. So this, what I call the synchrotron F function, is just kind of a smoothed result of blending together a whole bunch of cyclotron lines. And if you want to derive this from first principles, you can follow the discussion that is in Longair. So the next thing that we're going to, so this completes our discussion of single particle spectra. We've talked about the dynamics, we've talked about the mechanics and the kinematics. We've talked about the characteristic orbital frequencies, the gyro frequencies. We've talked about the radiation power that you get out of that. Then we talked about the relativistic time travel effects and the characteristic synchrotron frequency. And finally, we have the single particle synchrotron spectrum, which is this shape. It's something that peaks at this frequency. It's rare that you'll need to use this actual spectral shape, but this shape has an impact when we are considering multiple particles, because each of these segments, this 1/3 segment, all of this will show up when we start integrating over particle distributions. And that's going to be the focus of the next section.